This time we will focus on non-symbolic number, more specifically on non-symbolic number sense and its development. In the end of this session, you should be familiar with concepts such as ANS, approximate number system, subitizing, groupitizing, and number line. What do we mean when we are talking about non-symbolic number? Basically, we can divide the numbers into symbolic and non-symbolic representations of numbers. Symbolic numbers include numbers which are presented with number symbols, such as 6 and 72 in the box, as well as number words such as 4. Non-symbolic numbers are quantities, for example dots or different types of objects, such as apple in the box. This time we will focus more on numbers which are presented in their non-symbolic form. There has been suggested to be two different types of systems that track quantity and are thus related to so-called number sense. The first system is called approximate number system, ANS. The other system is related to tracking small quantities exactly, also called subitizing. I will explain the differences between these systems in the following and give some examples from each. Researchers have proposed that we are all born with an ability, the approximate number system, which allows us to discern between groups of objects of varying magnitudes. As the name says, this ability is inaccurate and represents the numerosity of a set of objects only approximately. For example, there are around 30 dots on the page. We are not the only ones having this ability, but we share this with some other animals, such as rats or monkeys, birds, and fish. This type of number sense is thought to be fundamental of learning culturally based verbal math. Verbal math would include an ability to count the exact number of dots using number words while I'm counting and to get an accurate number of dots. Next, I will show you some examples of so-called discrimination tasks which can be and often are used in research to tap the approximate number system. In other words, what kind of non-symbolic number sense a person has. These tasks are often computerized. For example, in this task, the participant will see a set of blue and yellow dots. The participant has to decide if there are more blue or more yellow dots. In the test, the participant's reaction time, how long does it take to make the decision, is recorded, as well as if the response was correct or not. For a good result, the participant should be pretty fast and also accurate. In this task, the participant needs to choose the panel with more dots. Responses are often given by pressing a button on the keyboard. In the third example, the participant needs to decide which side has more squares. The ANS tasks may vary in their difficulty level. Often it is easier to make the decision the greater the distance between the numbers is. If you look at the pictures of dots on the slide, most probably you would be quicker and more accurate in deciding that there are more blue dots in picture 2 compared to making a decision that there are more yellow dots in the picture 1. In picture 2, the numbers has greater distance between them than in picture 1. One reason for this can be that the representations of numbers, which are located closer to each other on the mental number line, may overlap. This overlap makes it harder to distinguish between two numerosities. If the representations of numerosities would be on the mental number line as in the picture, comparing numbers 4 and 10 would be easier as they do not overlap much on the mental number line. But comparing numbers of 8 and 10, that would be slower as they overlap much. When we look at how ANS develops along the childhood up to the adulthood, the performance in these types of discrimination tasks is related to the ratio between the number of items that we compare. For example, young infants can discriminate numerosities if the difference between them is big enough, such as a ratio of 1 to 2. Discriminating 8 dots from 16. Around the age of 3 to 4, with a ratio of 3 to 4, such as accurately and fast discriminating that 12 dots is more than 9. Most adults can discriminate numerosities with a ratio 9 to 10. So, the speed and accuracy of numerosity discrimination gradually improves as the child gets older. However, there are also some studies which have shown mixed results. One of the reasons for mixed results might be that different types of tasks have been used in different research studies, and the task may have been conducted with participants in different ways. There have been also some mixed results when ANS has been looked in relation to other math skills. Some studies have shown that the better the ANS, the better the overall math performance. This would then of course mean that if you have weak ANS, you would perform also weakly in overall math performance test. Some studies have looked the relation of ANS to specific math skills and found positive relation to counting and arithmetic skills. Some studies, on the other hand, have not found any strong relation between ANS and other math skills. The mixed results may come from the facts that the studies have been conducted to different age groups, so the relation may depend on the age of the participants. The effect of ANS has also diminished when other factors have been controlled in the study, such as the effect of working memory. Some researchers have suggested that the direction might be also the other way round, that when the children learn formal mathematics at school, it refines their ANS, becoming more precise. The current research findings suggest that having a core deficit in number sense, including thus ANS, is the primary reason for developmental dyscalculia. Often children with mathematical learning disabilities or developmental dyscalculia have weak ANS precision. It has been also found that symbolic number sense might have even bigger role than non-symbolic number sense. Tasks that tap symbolic number sense are, for example, comparison of two numbers which are presented in number symbols.